Okay, so it's already 10, and I think we can get started. All right. So this class, we're gonna continue our discussion on the single particle dynamics. So the reason why we're very interested in these single particles, like say drag force or all different types of other types of forces, is that people use these forces to remove particles. Okay. For example, when we in the coal-fired power plant, let's say it generates a lot of fly ash, then people might design very long duct, right? If you have a long distance of duct, then those larger particles can settle down by gravity. So in this way, you can remove some particles. And then we can also use the centrifugal force. Basically, it's called a cyclone. We're going to know that very soon. Okay, so cyclones are basically a cylindrical device where you push the airflow to rotate, right? To basically revolve around the center axis. So you will have a centrifugal force. Then the larger particles will just get spinned to the out wall of the cyclone. And we also will know electrostatic precipitator, which use electrostatic force. So all of these forces have to balance with the drag force. So that's why we have to start with the drag force in the beginning. So we can know how the other types of forces will affect the removal or control of these particular matter, right? So let's just do a quick recap of our last class. So basically last class, we learned about drag force, and we know that the drag force is a intrinsic force. It's not dependent on the external field. What it does is it tries to constrain the relative movement of a particle, right? Let's say if we have a very strong, very fast moving flow, airflow, and you have slow moving particles, then that's going to exert a drag force on the particle so that it tries to minimize the relative movement of the flow and the particle. So also know that if there is no drag force, then the raindrop will fall with a speed of 200 meters per second instead of 10 meters per second. So that's why drag force is very important, right? So we also use the drag force to design a lot of particle removal devices. So just a quick quiz about the concept of the drag force. So let's say that we have an airflow or wind. So basically the wind blows at a speed of 1 meter per second. Okay, it's a relatively slow speed. So we have two particles. So particle A has a speed of 1 meter per second in the same direction. Okay, and then let's say this is A. After 1 second, it moves to here. And B has a speed of 2 meters per second. Has a speed of 2 meters per second, right? It moves faster in the flow. Okay, so what is the relationship between the drag force on particle A and particle B? So let's quickly go through this quiz. All right. So remember, the drag force is dependent on the relative velocity, right? So if you consider the relative velocity between the particles and the flow, five more seconds. Okay, we'll stop here. I'm a little bit surprised about the results here. So as we mentioned, the drag force is dependent on the relative velocity. So what is the relative velocity between particle A and the flow? Zero, right? It moves with the same speed as the wind. Because it doesn't have any relative velocity, so the drag force is zero. Does that make sense? Okay, so only when the particle has a relative velocity, then there's a drag force. So then it doesn't matter about the particle B, right? Particle B moves faster than the flow, so there is drag force. So if you take the ratio between these two forces, it's going to be 0. Okay, I know that some of you also chose a 0.25, mainly because probably because last class we talked about the Newton's force, right? The Newton's equation is proportional to the relative velocity squared. Okay, this is the Newton's drag force, right? So probably you were thinking then it's just 1 squared over 2 squared, but again, this term here is the relative velocity. Okay, so if there's no relative movement, then there's no drag force. So the same thing can happen to a duct. Let's say we have a duct which has a flow upwards, right? And let's say inside the duct, the airflow has a velocity of 1 meter per second. Okay, so if there's a particle that can levitate, let's say the particle, because of its gravity, right? If there's a particle that can levitate in the flow, although its absolute velocity, let's say VA absolute velocity is 0, but the relative velocity is not 0. So there is still drag force in this scenario. Okay, so drag force actually balanced with the gravity.
Excuse me, Dr. Wang. What's the difference between normal velocity and relative velocity? Did you mean about relative velocity equal distance divided 2 time?
So let me introduce relative velocity and absolute velocity then. So let's say we have a train, okay, that goes in this direction. So the absolute velocity is just to the system. Let's say you were standing here, right? The train moves with a speed of 1 meter per second. So this is the absolute velocity, right? And then if there's an object on the train that moves with the train, so the absolute velocity of this object is also 1 meter per second.
I get it. Thank you. Yeah.
Yeah, right? So the relative velocity is 0. Okay, does that make sense for this problem, right? So that's why we need to choose 0 here, and it's not infinity or 0.25 or 0.5, okay? All right, so since I'm a little bit surprised about the results, and I've introduced the reason for this, can we just do another quick poll? Just trying to make sure that you guys know the concepts, all right? Okay, we'll just stop here. All right, I'm still seeing a few choosing 0.5. So, I mean, try to understand this relative velocity concept. Okay, if you don't, if you have any questions, you can feel free to ask me or ask your classmates. We'll just stop here. All right, so let's just continue. So last class, basically we introduced the Newton's form of the drag force. We know that the force can be written by basically 1/2 rho F V infinity, oh, not V infinity, VR square AP and CD, okay? So we mentioned that the rho F is the fluid density. all right? BR is the relative velocity. So AP is the cross-section area. And CD is the drag coefficient. Okay. So at that time, this equation actually works pretty well in predicting the force on the particles, and it's actually also quite straightforward, right? If you consider about what is the drag that exists on a object, right? So the larger the cross-section area, the larger the drag force, and the more dense the fluid, the larger the drag force. So that's why the drag force in water is going to be higher than the air, right? Also, the higher the relative velocity, the higher the drag force. So also mention that the drag coefficient that's at the end is not a constant, right? It's a function of the Reynolds number, right? So later on, we showed this plot here, which basically tells you what is the relationship between the Reynolds number and the drag coefficient. Okay, this is CD. So actually in this plot, it's also in your textbook, it's figure 3.6. In this plot, it's showing 3 different types of particles. So we have the spheres, we have the cylinders, and we have the disks, okay? So for particles with different geometry or shape, they're going to have different types of drag force. Let's say, although we have a particle that has the same volume, let's say 1 centimeter cube, okay? Then for a cylinder, the cross-section area will be different compared to the sphere. That's why its drag force is also going to be different, right? It really depends on how it's flowing in the fluid flow, right? But in this class, we're just going to deal with the spheres, okay? We assume that all the particles are spheres, and it actually helps us solve a lot of fundamental questions in particle removal, right? So further, if we consider or look at the relationship between the drag coefficient and the Reynolds number, what we can notice is that probably above Reynolds number larger than 1,000. So the CD is close to a constant, although it has a dip at the end, right? But in this region, basically, we're not going to deal with a lot of processing in this region. But here, you can consider that as a constant, okay? And when Reynolds number is below 0.1, so you can see that there's a kind of a linear relationship between the drag coefficient and the Reynolds number, okay? And this is also in the log scale, right? So then people actually find out that in this region, or in this regime, where Reynolds number is below 0.1, the CD is equal to 24 divided by Reynolds number. Okay, so that's why when you plot it in the log scale, it's going to show you a slope of 1, basically -1. Okay, so now actually in this course, most of the scenario we're going to deal with are in this region. Okay, so it further simplifies this problem. So what we can do is we can just plug in this CD number into the Newton's equation, right? Remember here, we can plug in the CD and we can find out what the result is, right? So we can see the drag force is equal to 1/2 rho F VR squared, and VR squared AP and CD. Okay, so we know that for a sphere, the cross-section area is just the area that has a circle or has a basically has a radius of the particle diameter, right? Or the particle radius. Let's say the particle diameter is in is this one, it's dp, right? Then basically the cross-section area is just this area, right? So that's gonna be pi over 4 dp squared, right? So we can try to plug in all of these parameters. 1 over 2 rho f VR squared AP, that's pi over 4 dp squared. So CD is 24 divided by Reynolds number. We know that the Reynolds number I think it's probably, so can you see my screen moving? No, I think it's probably stuck. Let me just try restart it. All right. Okay, now it should be good. All right, so we know that the Reynolds number can be written as VR rho f dp divided by the gas viscosity, right? So we can basically plug this in and see what happens. 1 over 2 rho f VR squared pi over 4 dp squared 24 divided by VR rho f dp multiplied by mu. Okay, so this is a basically a set of parameters, and actually a lot of them can get cancelled, right? For example, rho f can get cancelled, right? We have VR, one of them is cancelled, right? 2, 6, that's 8. This is going to be 3, right? And then one of the dp can get cancelled. Okay, so if we write it out, that's going to be 3 pi mu dp multiplied by VR. Okay, so this is what we get from the basically the Newton's equation regarding the drag force when the Reynolds number is below 0.1. So when the Reynolds number below 0.1, basically in the fluid dynamics, we also call this as laminar regime, right? And when the Reynolds number is above 1000, that's turbulent regime. So because the turbulent regime is too complicated, right? Normally involves a lot of equations. So in this class, we're gonna deal with the laminar regime only, right? So that's why we can get this equation here. So if you remember at the beginning of the class, I said there are two things that, I mean, it's the minimum requirement for this class, right? So one thing is about the definition for the particle, for the PM. That's called a stable cluster of molecule, right? So that's the thing that I want you to memorize. So the other thing I want you to memorize is this equation, okay? It's just this equation. So it's 3 pi mu dp multiplied by VR, which is the drag force. Okay, I'll put a star here. Because with this equation, you can solve for a lot of particle movement, particle capture problems, okay? So we'll show later how why this equation is important. So basically, this is what people get from the Newton's form, and people have realized this maybe 200, 300 years ago. It's just based on pure analysis of the physical terms, right? And we can get this elegant equation here. So what happens is that later on, when people discover all the differential equations, calculus, right? So people can really try to look at the physics that's happening in the system. So probably in fluid dynamics, you also have learned the basically what happens when a fluid flow will flow past by a sphere. So this is a solid sphere, right? We have a fluid flow that goes this way. And then what we know is that the flow is going to basically get diverted by the sphere here, right? And then for this problem, or this is a problem called Stokes problem, okay? So for this problem, people can get analytical solution. People can get analytical solution about what is the velocity profile that's surrounding the particle. What is the pressure? What are the different types of forces that's applied onto the particle? So I'll just write out all the equation here, but I think you can find it from your earlier textbooks, okay, regarding this type of problem. So people try to use the Navier-Stokes equation. So Navier-Stokes equation is the original form or original differential equation to solve for all different types of fluid dynamics problems, right? But for this problem, because it's symmetric, right, we can greatly simplify this fluid flow problem, and then we can get a analytical solution. So what happens is, for this equation, we have Reynolds number. If we assume that Reynolds number is below 0.1, which is in this regime, then we can solve for what is the pressure that's added onto the particle. So if you consider what are the forces that's brought by these fluid flow, there are two types of forces, right? So one of the forces is basically directly perpendicular to the particle, right? So we call this force as a pressure force, or the normal force, right? So the other types of force is the tangential force. So when the fluid flow passes by, because it's viscous, right, it's going to drag the, basically create a tangential force that's adding onto the particle. So then if we want to solve for all the force that's on the particle caused by the flow, we need to combine these two forces together, right, add them up. So what happens in this problem is that people can solve for what is the normal force or the perpendicular force. So that's related to the pressure. The pressure can be calculated by P0 minus 3/2 mu VR divided by R. Okay. So basically this R here is the particle diameter or the particle radius. And this R here is any distance. Basically any distance from the center of the particle. Right? So the VR, again, this is the relative velocity. All right. So we can also solve for the tangential force, or the tangential, basically this is force direction, right? That's basically perpendicular to this normal force. 3/2 mu VR divided by R over, okay, sine theta. So this theta angle, this angle here is the theta, okay? So then if we consider the tangential force directly at here, if we want to look at the tangential force at here, then that's going to be 0, right? Because it's not pushing the particle to the left or to the right. It's at the center of the particle. And the tangential force at here are going to be 0. So if you plug in theta equal to 0 or 180 degrees, right, you're going to get 0 here. So basically, people can solve for the analytical form of these two forces, and then we can calculate what is the total force. So the total force is just an integral of these two basically force components, okay? So I'll skip the integration term. And what people can find out is that if you integrate them, probably just write out the equation here. I minus P R equal to R cosine theta A plus okay, so these are the two integrals, right? If anyone is interested, you can plug in these two equations and see whether the result is correct, okay? So when people find out is that the total force is equal to 4/3 pi r to the third rho g plus 6 pi mu r v vr. Okay, so this is a final form. So let's just look at these two terms. Okay, so one of the term, it looks actually quite familiar, right? You have 4/3 pi r to the third. We mentioned that the r here is a particle radius. So this term is the volume of the particle, right? This is volume. So the rho here, again, rho here is the fluid density, okay? So if you take this term, okay, this is just the buoyancy. And this makes sense. If we put a particle in the water or in any fluid, the fluid is going to create this buoyancy to the particle. And if you look at this term here, this is 6 pi mu r v infinity, or r, basically vr, relative velocity, okay? This looks quite familiar. So 6 multiplied by r is just 3 pi mu dp multiplied by vr, okay? So this is the equation that I want you to memorize, right? This is exactly the Newton's form, right? So basically, this analytical method was done in the year of around 1890, okay, when people are already quite familiarized with the calculus, differential equation, integration. You can see that we get exactly the same form of the drag force. Okay, that's 3 pi mu dp multiplied by Vr. So this is the most or the central equation when we consider about the particle movement, right? Basically these equations, or we can find out that Newton's form and the Stokes form, they actually match each other when they're in the laminar flow region, when Reynolds number is below 0.1, okay? So again, this is, if you consider the year here, it's still quite early, right? So at that time, people didn't know what the air is composed of. There's no way we can know how large is a particle or how large is a molecule. So then people start to realize that in the atmosphere, there are a lot of very small particles, okay? So here, what we're considering is that this can be any sphere. This can be like a baseball, right? It can be a potato if that's round enough, right? So, but if we consider about these suspended particles in the air, some of them can be very small, right? So when they are small to a size that you cannot treat the fluid, treat the gas or air as fluid anymore. So let's say, what happens if a particle that has a similar size compared to molecule? Okay, so we know that all of these force that's added onto the particle are just because of the bombardment. Basically, collision between the molecules and the particle here, right? So when the particle size is small enough, it's a small particle, So the fluid molecules cannot be continuous anymore, right? It's just single collisions, and a lot of these molecules originally it might get collected onto the particle, they might miss the particle. Okay, so that's why people further introduce a coefficient. So basically, under this situation, when particles are very small, the drag force Fd will be smaller than expected. Mainly because the collision between the molecules and the particle, or the probability, becomes lower, right? So that's why people further introduce a correction factor. So now the final form that we have nowadays when we try to calculate the particle movement is 3 pi nu dp Vr divided by c. Okay. So pay attention that this c term here is called the slip correction coefficient. Okay, slip correction coefficient. So this c is not equal to cd. Okay, the cd we introduced earlier, that's drag coefficient. Okay, so the drag coefficient is this term. All right, the drag coefficient depends on the Reynolds number. In the larger Reynolds number regime, CD is a constant, right? In the lower Reynolds number regime, that's 24 over Reynolds number. But here, when we discuss C here, it has to be in the Stokes regime, where the Reynolds number below 0.1. Okay, so C is not equal to CD. Actually, C, you can calculate that with the equation. C is calculated by 1 plus 2 lambda dp, 0.257. Okay, this is a very long equation, but actually this equation was collected purely based on observation. Okay, so these are all the fitted numbers from people's experiments. We just did so many of these experiments to characterize this coefficient here. All right, so in this equation, the lambda, that's the mean free path. Mean free path of the molecules, or I should say air molecules. Okay, mean free path is just the average distance. We know that the air molecules are always colliding with each other, right? So when they're not colliding with each other, they travel by straight distance until they collide with another molecule here, right? And then they will move to some other location and then collide with the next molecule, right? So the mean free path is just the average distance between two collisions. For example, it's just the distance from here to here, from here to here, from here to here, and then we just average them all, right? So that's the mean free path. So in the air, under normal condition, this mean free path is around 68 nanometer. So basically, the molecules can travel along a straight line for 68 nanometer until it collides with the next air molecule. Okay. So basically, in this equation, when we calculate the slip correction factor, we compare the relative magnitude between the mean free path and the particle size. Okay. So we have a lot of other following terms here, but let's just look at two extremes. Okay. Let's say when dp is much larger than lambda. So this is in the very large particle regime. This is in the potato regime, okay? Very large particle. So what happens at that condition? Let's say we just look at these terms here, right? So for this term, lambda is much smaller than dp. dp is much larger. So this is almost equal to 0, right? So inside this term, you see 1.247, that's just a constant. 0.4 is a constant. So exponential dp over lambda. So this is going to reach to almost infinity. And this whole term goes to negative infinity, right? So the exponential term of negative infinity is 0. Okay, so if you look at this term, c will almost equal to 1. And this makes a lot of sense, right? This is in the larger particle regime. C is equal to 1, right? C is equal to 1. Then we know the drag force still follows the Stokes equation, follows Newton's equation, right? In the larger size range, C is just equal to 1, right? So when in the very small size range, let's say much, much smaller than lambda, you know, let's say lambda is equal to 68 nanometer. Let's say if a particle has 1 nanometer size range or 1 nanometer particle size, okay, then that's going to be much smaller than lambda. So then if you look at C, now we know that 2 lambda over dp, that's going to be very large. We'll go to almost infinity, right? And if you look at the terms inside, this is constant again, constant, right? In this term, dp divided by lambda, that's just 0. Right? dp much smaller than lambda, this is 0. So exponential of 0, that's equal to 1. So this whole term will almost equal to 2 lambda divided by dp multiplied by 1.24257 plus 0.40 multiplied by 1. Okay, so that's going to be 2 lambda dp multiplied by 1.657. All right, so this is our C when the particle size is much smaller than the mean free path. Okay, so basically you can see because this term it's becoming larger, right? Lambda divided by dp, that's becoming larger as particle size goes smaller and smaller. So the C will become larger, the drag force will become further smaller. Right? Basically, this is the process when the particle size is very, very small, how it's going to affect the drag force of the particle. So here I'm also showing a table. This is the relationship between the particle size and the slip correction factor. Okay, so you can see when the particle size is very large, 10 micron. I mentioned that lambda is 68 nanometer. When the particle size is 10 micron, C is close to 1. Okay, so only when, let's say, particle size is below 1 micrometer, when particle size is below 1 micrometer, you can start to see that C become larger and larger. And this is going to affect our calculation for the drag force. Okay, so you'll get more practice on this problem in your homework, right? So now with the drag force, with the exact equations, we can now try to look at what is really happening during the gravitational settling. Let's say the raindrop falling down or the particulate matter falling down, okay? So basically what happens is that we have Newton's second law, right? We have m multiplied by a. Say this is our particle, has gravity, and we can ignore about the buoyancy, let's say, and then it has a drag force. Okay, so ma is going to be equal to mg minus the drag force. So we know the drag force is equal to 3 pi mu dp multiplied by v divided by c. Okay, this is our drag force. So on the left hand side, we have m, basically dv dt equal to mg minus 3 pi mu dp v divided by c. So here, since we're talking about gravitational settling, we assume that the air is stagnant. So there's no airflow. So that's why VR, the relative velocity, is going to be equal to the absolute velocity of the particle, right? Because the air doesn't move at all. So now this is just a differential equation, right? So the particle mass is not a function of the velocity. So we can just cancel m on both sides, right? So we further know that m is equal to pi over 6 dp to the third rho p, right? It's just the volume multiplied by density. And then we can plug in this expression in here, okay? So dv dt equal to g minus 3 pi mu dp v divided by pi over 6 dp to the third rho p multiplied by c. Okay, so next class we're going to talk about the how to solve for this differential equation. But right now, let's just look at how this equation affects the final velocity. Okay, so what I mean by final velocity, so people have a term for this final velocity that's called the terminal velocity. So for example, when the raindrop falls down from the sky, right? Initially it's accelerating, right? Mainly because it has enough mass, right? It has the drag force, it has the gravity, but the drag force is not going to be able to balance with the gravity. But then as it further accelerates, you see the drag force scales with the velocity here, right? So the drag force will become larger and larger until at one time point, the drag force balance with the gravity, okay? So when they balance, we know that there's no further change of the acceleration or change of the velocity. So we reach to a constant velocity settling down, and we call that constant velocity as the terminal velocity, okay? So in this equation, what that represents is just dv dt equal to 0, right? So there's no change of velocity anymore, or the force already balanced there, right? So in this case, we can actually solve for this terminal velocity. So if this term is equal to 0, then we have, let's say first we will cancel these pi here, and then one of the dp will get canceled, and this thing will get to 18. So we can calculate that v is equal to say dp squared rho p g c divided by 18 mu. Okay. So this is
Dr. Wang,
yes.
please, dv divided dt. Did you mean this called terminal velocity?
dv dt is the acceleration,
Okay.
the change of the velocity, right? So
Okay.
this thing, yeah, comes from the Newton's second law. It's the a here, a term. Yeah, feel free to jump in, ask questions. I really want you to know about these equation derivation. It's a lot easier if we know how they're being derived than to just memorize the equation and then use the equation to solve problems, okay? So I hope during this process, you can know how people actually try to understand a lot of PM removal devices or PM trajectories or dynamics, okay? So basically, this equation here is called the terminal velocity. We also call that as VT, okay? So you can see that VT actually, when the particle size is large enough, when the C is close to 1, VT will scale with the particle size square, okay? So what that means is, let's say if we compare a 1 micrometer particle and a 10 micrometer particle, so their settling velocity will almost scale, or their ratio will almost equal to 100, because the settling velocity scale with the particle size, right? So the 10 micrometer particle will settle 100 times faster compared to the 1 micrometer. So now you see, that's why larger particles, they will just naturally settle down. It's just very small particles that they're very difficult to get rid of, right? So, so this is terminal velocity. So here in your textbook, it actually shows you a graph of the terminal velocity for particles with all different sizes. Let's say on the x-axis, it's the spherical particle diameter, right? It starts from 0.1 micrometer to 30 micrometer, and then further above here, it starts from 10 micrometer to 3,000 micrometer, which is basically 3 millimeters. 3 millimeters is already very observable. You can see those particles now. So on the y-axis, it shows the terminal settling velocity. So it just calculates based on this equation, okay? And also, I shouldn't say it's based on this equation, but it's originally everything is based on the drag coefficient. Okay, so we were just trying to understand in the Reynolds number below 0.1, but for the results shown in that graph, it considers all the Reynolds number conditions, right? But in this graph, we can briefly look at or find out what is the settling velocity for particles with different sizes. Let's say we have a particle that has a density rho p of 1. So this 1 here means the density is equal to the water density, okay? People also call this as specific gravity. So basically, if a specific gravity equal to 1, then it just means that the particle density, or the density of this species, is 1,000 kilogram per meter cube, which is water density. Okay, if it's equal to 2, then that's going to be 2,000. Okay, so let's say if we're interested in a particle with a size of 2 microns, what is its settling velocity? It's going to be here, right? Going to be here, and then if we trace here, it's going to be 0.015. Okay, so pay attention that for this curve, you're going to look in this direction, as shown by these arrows here. Okay, for these curves, you're going to look at this direction. Okay, so if we use this curve here, then you can see that 2 micrometer particle has a velocity of 0.015 centimeter per second. Okay, so if you consider that velocity, that's very small, right? And then if we're interested, let's say for 600 micron particles, very large size, right? And then it's basically here. And then if it has a specific gravity of 1, then you can see the settling velocity is somewhere around 260 centimeter per second. Okay, that's 2 meters per second, which is already very large. So we say that this class is actually quite close to the COVID-19. It's, I would say we have a lot of application for the PM or particulate matter knowledge on the transmission of this disease. Mainly it comes from this concept. Okay, so I think by looking at the news, we hear a lot of terms about droplet transmission or airborne transmission. So when CDC and WHO first come out with the transmission guideline of this virus, what they call is that, what they say is that the transmission of the virus is mainly done by droplet transmission. Okay, so that's why all of us wear masks, because masks can block these droplets very effectively. So what is the definition of a droplet? Okay, so in their medical field, droplets are basically particles, suspended particles, aerosols, or PM, that are more than 5 microns. Okay, their size is larger than 5 microns, we call them droplet. So also here the rule that we apply, that's 6 feet rule or 2 meter rule. So now we can know what is the settling velocity. Let's say if someone sneezes or speak, what is the settling velocity of these 5 micron particles, right? By using this plot. So you can see that the settling velocity is somewhere around 5 micron, 0.08 centimeter per second. Okay, so if a person has a height of 1.6 meters and the settling velocity 0.08, you know that the droplet can stay for more than 2,000 seconds. So do you think 6 feet rule is enough? Right? 2,000 seconds more than half hour, right? So there are some misunderstandings regarding the movement of droplets, right? So basically, next class, we're not going to talk more for equation derivation. So in our Monday's class, you guys will watch an online lecture by Professor Lindsay Marr. So he's an aerosol scientist on this topic. She has a lot of research backgrounds on these topics, and she has an online video or lecture. So you guys will find out the link. So that lecture is probably around 30 minutes. So you can know how our knowledge is being applied onto this pandemic here, all right? So that's all for this class. Let me know if you have any questions.